Hello students, in past few classes we have studied the unit number first. The unit number first was comprised of two main chapters. The first one chapter was the coordinates, and the second chapter, which is actually the serially fifth chapter in the book, was comprising of transformation of coordinates. In the first chapter, that is the coordinates, the main articles that we have studied were the angle between two lines, direction cosines of a line, relation between direction cosines, projection on a straight line, and angle between two lines. Whereas in the chapter number 5th, that is in the chapter transformation of coordinates, the main articles that we have studied were the change of origin, then the change of the direction of axis, and lastly the relation between the direction cosines of three mutually perpendicular lines. So like such we have completed the first unit in past few classes. Now in the today's class we are going to start the second unit from this paper, and the title of this second unit is the plane. So in this second unit we are going to study the definition of a plane and various properties of the plane, and particularly in today's class we are going to study the definition of a plane and one important theorem about the plane, as well as we'll solve one example at the end. So let us begin with the definition of a plane. We know what is meant by a plane. Now we'll define a plane by mentioning the characteristics property. That property is a geometrical locus is a plane if it is such that if P and Q are any two points on the locus, then every point of the line PQ is also a point on the locus. I will write down this characteristics property of plane here. A characteristics property defining a plane is a geometrical locus. A geometrical locus. A geometrical locus is a plane. It is said to be a plane. Is a plane if it is such that if P and Q, these are the points, therefore we will write them in capital case. If P and Q are any two points on the locus, then every point of the line PQ line PQ means the line joining points P and Q is also a point of the locus. So like such plane is defined. I will repeat. See here, a geometrical locus means set of points which satisfies certain condition is called as a locus. So a geometrical locus is a plane if it is such that if P and Q are any two points on the locus, then every point of the line PQ is also a point of the locus. So like such, the plane is defined. Diagrammatically, we will see what a plane means. Suppose we have a geometrical locus. The geometrical locus is as such. Okay, and now this will be a plane if we take any 2 points from this locus, and if the line joining those 2 points always lies in this locus, then it will be a plane. So if we consider the points P and Q as such, then the line joining these points P and Q obviously completely lies in this locus. Here it is so. Next we will consider another points. Let this is one point and this is another point. Then we will draw a line joining these 2 points. So the line will be as such, and we observe that this line completely lies in this locus. Means the line joining any 2 points of the locus, if it completely lies in the locus, then that locus is a plane. So it is verified also here. Next, but if we consider the points as I am showing here, that one point is suppose here and the other point is here, and if we join these 2 points by means of a line, then let us check whether that line completely lies in this locus or not. Okay, so we'll draw a line joining these 2 points. Then a line joining these 2 points, if you observe, then some of the points of this line lies outside this locus, as can be seen here. Okay, so therefore the line joining these 2 points of the locus do not lies completely in this locus. Therefore, as per our definition, this locus cannot be a plane. So it is not a plane. Okay, next one. Now let us consider another locus. Suppose we have a locus as it is shown here. Now take any 2 points from this locus. One point is suppose here and the another point is here. Join them by means of a line. Then you observe that this line completely lies in the locus. So as can be seen here, this line joining any 2 points of this locus lies completely in the locus. You can take some other points also, as I am considering here. If you consider these 2 points, then the line joining these 2 points also lies completely in the locus. Therefore this locus is a plane, whereas this locus is not a plane. Now after this defining property of the plane, and by considering these 2 diagrammatic presentations, now we'll go for the first result of this chapter, and it is the general equation of first degree. First of all, we'll see what is meant by the general equation of first degree in 3 variables x, y and z. The equation ax plus by plus cz plus d equal to 0, where a, b, c and d are constants, means real numbers. This will be a first degree equation in 3 variables, provided that a, b, c, all 3 coefficients should not be 0 at the same time, which means that one of these 3 coefficients a, b, c can be 0, or 2 of them can be 0, but all 3 coefficients a, b, c should not be 0 at the same time, because if all 3 coefficients a, b, c becomes 0 at the same time, then obviously this will become a 0 degree equation. Therefore, the condition for this equation to become a first degree equation in xyz is that not all a, b, c are 0 at the same time. Not all a, b, c are 0 at the same time. And this condition can also be written in the form that is a square plus b square plus c square. This summation is not equal to 0. As we know that a square plus b square plus c square, this summation will be equal to 0 only when all a, b, c are 0 at the same time. Okay, so therefore the equation ax plus by plus cz plus d equal to 0 will be a first degree equation if a, b, c are not 0 at the same time, which means that if a square plus b square plus c square is not equal to 0. Now, in the first result, we are going to prove that every equation of the first degree in x, y, z represents a plane. Every equation of the first degree in three variables x, y, z represents a plane. That we are going to prove now. Okay. So proof is simple. We'll prove this one. So first of all, we have the general equation of the first degree in x, y, z as ax plus by plus cz plus d equal to 0, where a, b, c are not all 0. A, b, c not all 0 at the same time. So that is, this can also be written as, that is a square plus b square plus c square. This summation, a square plus b square plus c square, this summation should not be equal to 0. Okay, next. Then, as explained just now, the locus of this equation will represent a plane if it satisfies this defining characteristics property. Okay, then the locus of this equation will be a plane if every point of the line joining any two points, suppose the points are P and Q, if every point of the line joining any two points on the locus also lies on the locus. So, for that purpose, we have to take any two arbitrary points from that locus. So, let P and Q having coordinates x1, y1, z1 and x2, y2, z2 respectively be any two points of the locus. Now, if P and Q are any two points of the locus, then obviously they will satisfy the equation of the locus. Equation of the locus was ax plus by plus cz plus d equal to 0. And as we are supposing that P and Q are the points of this locus, therefore coordinates of these points will satisfy this equation, and therefore we will get a into x1 plus b into y1 plus c into z1 plus d equal to 0. That is ax1 plus by1 plus cz1 plus d equal to 0. And similarly for the point Q, we will get ax2 plus by2 plus cz2 plus d equal to 0, and that will denote by the equation number second. Okay, so as the points P and Q lie on the locus, therefore they will satisfy the equation of the locus, and therefore we have obtained equations 1 and 2. Next, now we will multiply the equation second by the constant k and add it to the equation number 1. So multiplying this equation second by k and then adding to the equation number first, we will get ax1 plus by1 plus cz1 plus d plus k into ax2 plus by2 plus cz2 plus d and equal to the right hand side 0. Okay, we'll simplify this one. So we'll get ax1 plus kax2. From these two terms, we'll take the a common. Therefore, we'll get a into, it is x1 plus k into x2. x1 plus k into x2 plus, now from the second terms of both the equations, we'll take b common and we'll get b into y1 plus k into y2. So the next term is b into y1 plus k y2 b into y1 plus k y2. Next term is plus c into, it is z1 plus kz2, z1 plus kz2, and the last one term is plus, it is d into 1 plus k, d into 1 plus k. This is equal to 0. Okay, so like such we'll get. Now next one, now we don't want this 1 plus k in the last term, so we'll divide throughout by this term 1 plus k, and then we'll get a into x1 plus kx2 divided by 1 plus k, which is written here, a into x1 plus kx2 divided by 1 plus k, plus the second term will be b into y1 plus ky2 divided by 1 plus k, which is written here, plus third term is c into z1 plus k z2 divided by 1 plus k, which is written here. And finally, the last term will be simply d into 1 plus k divided by 1 plus k, which is equal to simply d, and equal to the right hand side is 0 divided by 1 plus k is simply 0. Okay, this. Now next one. This is our equation number 3. If you observe this equation number 3 carefully, then we observe that this equation is satisfied by the point having coordinates x1 plus kx2 upon 1 plus k, y coordinate y1 plus k by 2 upon 1 plus k, and the z coordinate z1 plus k z2 upon 1 plus k. So, by this equation 3, we observe that the point x1 plus kx2 upon 1 plus k, y1 plus k by 2 upon 1 plus k, z1 plus k z2 upon 1 plus k satisfies the equation of the given locus. Equation of the given locus was ax plus by plus cz plus d equal to 0. So, this point satisfies the equation of the locus. And if you remember, this is nothing but this is the coordinate of any point which lies on the line joining points P and Q. So therefore, we have shown that this point satisfies the equation of the given locus, which means that every point on the line joining the points P, x1, y1, z1 and Q, x2, y2, z2 also satisfies the equation of the locus, means is also on that locus, and which then by the characteristics property of the plane means that locus ax plus by plus cz plus d equal to 0 with a square plus b square plus c square not equal to 0 means this locus given by the first degree equation in xyz represents a plane. So therefore, we have considered a general equation of the first degree in xyz, and we have shown that equation represents a plane. So therefore, we have proved this first one result. Hence, we have concluded that every equation of the first degree in xyz represents a plane. So like such, we have proved this first result of this chapter. Now, there is one example based on that we'll also solve. So the example is, find the coordinates of the point where the plane ax plus by plus cz plus d equal to 0, a square plus b square plus c square not equal to 0 meets the three coordinate axes. So we'll solve this example. Here the equation of a plane is given to us, and we are asked to find the coordinates of the point where this plane meets the coordinate axis. Coordinate axis means x-axis, y-axis, z-axis. So we'll solve this one. So solution is, given equation of plane is, so equation of plane is ax plus by plus cz, ax plus by plus cz plus d equal to 0. This is the equation of the given plane, where obviously a square plus b square plus c square is not equal to 0. So with a square plus b square plus c square is not equal to 0. Next one, we have to find the points of intersection of this plane given by equation 1 with the coordinate axis, means with the x-axis, y-axis and z-axis. Now, for that purpose, we are going to use the equations of the coordinate planes, that is of the x-axis, y-axis and z-axis. So, we have equations of the, first of all, x-axis. Equations of the x-axis are, y equal to 0, z equal to 0. That we have discussed in the preliminary part. Okay, as on the x-axis, y and z coordinate of every point is 0. Therefore, equations of the x-axis are y equal to 0, z equal to 0. Therefore, putting y equal to 0 and z equal to 0 in equation 1, we get, as the point of contact is a point which is on the x-axis as well as on the plane, so it will satisfy equation of the plane as well as equation of x-axis. So therefore, we have to put y equal to 0, z equal to 0 in the equation of the plane. So therefore we will get a into x as it is plus b into 0 plus c into 0 plus d equal to 0, which is nothing but simply ax plus d equal to 0, which implies that ax is equal to minus d, and ax equal to d implies that x is equal to minus d by a. Okay, so therefore the x coordinate of the point where the given plane intersects the x-axis is minus d by a. Therefore point of contact of given plane with x-axis is, so that point is having the x coordinate minus d by a. So x coordinate is minus d by a. Y and z coordinate are obviously 0 as that point is on the x-axis. Therefore the y and z coordinates are obviously 0. So like such we have obtained the point of contact of given plane with the x-axis. Now similarly we can say that the point of contact of given plane with the y and z axis also. Okay, so similarly the points of contact of given plane with y-axis is, for finding the point of contact with y-axis, obviously we have to put the x equal to 0 and z equal to 0 in the equation of the plane, because equations of the y-axis are x equal to 0, z equal to 0. So therefore if we put x equal to 0 and z equal to 0 in this equation of plane, that is in the equation number 1, we will simply get by plus d equal to 0, which means that by is equal to minus d, and which gives us y equal to minus d by b. So y coordinate of that point of contact will be minus d by b, and therefore as the x and z coordinates are already 0, therefore we have that point of contact with the 0, minus d by b, 0. This is the point of contact of given plane with the y-axis and with the z-axis, is, again observe here. So equations of z-axis are x equal to 0, y equal to 0, as every point on the z-axis has its x coordinate 0 as well as the y coordinate 0. Therefore if we put x equal to 0 and y equal to 0 in this equation of the plane, therefore we will get cz plus d equal to 0, which implies that cz is equal to minus d, z equal to minus d by c. So therefore the z coordinate of the point of contact will be the minus d by c, and as that point is on the z axis, therefore its x and y coordinates are obviously 0. Therefore the point of contact of the given plane with the z axis will be the point 0, 0, minus d by c. So this is that point. So hence in this way we have obtained the points of contact of given plane with the x-axis, y-axis and z-axis, and the points of contact are: with the x-axis the point of contact is minus d by a, 0, 0. With the y-axis the point of contact is 0, minus d by b, 0, and the point of contact with the z-axis is 0, 0, minus d by c. So like such we have solved this example. So in today's class we have defined the plane by mentioning the characteristics property of plane. Then we have proved one important result on the plane, as the every equation of the first degree in x, y, z represents a plane, and at the end we have solved one example based on it. So we'll stop here in this class and we'll continue in the next class with the converse of this result. So we'll stop here. Thank you.